Okay, so we're recording. Welcome back. I hope everybody had a good weekend. We had some lovely weather. Let's see. Here's where we left off. We were almost done with this section, not quite. So there are a category of questions that the book calls distance problems, which makes sense. How do you find the distance from a point to a line? How do you find the distance from a line to a plane? How do you find the distance between two parallel planes? There's a million different combinations of these kinds of things. Bit of an overstatement. But there are nevertheless more to that we could hypothetically consider than I'm actually going to go through. I'm just going to show you some examples of the kinds of tricks that you can use in various different cases. First one we're going to talk about, if you have a point and you want to compute the distance to a line. What's the distance from the point to the line? Now, to be clear what that means when we say distance from a point to a line, there are lots of different ways to get from a point to the line. Which one of these distances is the distance? It's always understood, usually unspoken, that what we mean is the shortest distance from the point to the line, namely the perpendicular distance. Okay. All right, so how do we go about doing this? There's a nice little trick here. Oh, I should clarify. This is assuming that our line is given to us parametrically, namely that I know a point on the line and that I know a direction vector, so a vector v here parallel to the line. Okay, so that being the case, here's the move. The point that you're given, the point from which you want to compute the distance to the line, consider also the point that you're given that's on the line and subtract. Right? That gives you a vector like this. Then, remember, we have a pre-existing formula for how to compute this thing called the projection. Right? The projection is something that we discussed last time. There's a nice little pat formula for it. It involves a dot product and a unit vector. So go ahead and compute that projection, and then realize the thing that you're actually interested in, this perpendicular distance. Right? Let me say that vector whose magnitude is the perpendicular distance. You just notice that vector is the W vector minus the projection. And it's all over but the shouting at this point, right? The distance that we're actually looking for here, the actual length there is just in the magnitude of that of that D vector. Yeah. Everybody see how that works? That's a nice little trick, right? Use the projection to kind of fix. You might say you start off with a completely wild guess of which point to use, and in some sense, the projection is a way of fixing it and saying, you missed. You shouldn't have been over here. You should have been over here, and the projection just helps you fix your naive first guess. Okay. All right. Next example. Now, this is the same scenario. We've got a point. We want to find a distance to a parametric line. I'm going to give you a different trick. This is a very clever trick. I did not think of this on my own. Somebody showed this to me when I was probably around your age. But it's really clever. I wish I'd thought of it. It's a super slick move. When you want to compute something, very often the thing to do is to compute something else, such as this area, two different ways. That sounds silly. Why would we twice compute something that we don't actually want? It seems counterproductive, right? But if the thing that you want, if that distance in this case, if that shows up as a participant in one of those calculations, then we get to say, okay, well, I didn't actually care about the area in the first place, but just because of those area arguments, now I have an equation involving these other things, and I can just solve for what I want. It's a slick move, right? So don't go straight at what you're trying to compute. When you're using this strategy, what you do is just get it involved what does it relate to in any way, right? And then compute that thing some other way. And then you can kind of piece it together. So the argument that we're making here, let's see here, computing the area. First, I argue that it's what you might call height times what you might call the base, right? Just height times base, old high school geometry formula there, no big deal. Now, alternatively, if I can get that to, come on. Maybe I can come at it from down here. There we go. Alternatively, I can compute that area by saying, okay, well, I know these two vectors, as previously discussed, and the parallelogram's area is the magnitude of the cross product. And so the two separate calculations for area that we, again, is not what I actually want. These two separate calculations themselves are not that bad, and we just notice that it involves the thing that we do want to compute, and then again solve. So slick move. I wish I'd thought of it. Questions? Oh yeah. Mm-hmm.
I'm confused because so the magnitude of the p vector is like it's just like a linear length. I don't see how that can be equal to P cross W, because P cross W covers an entire like parallelogram or rectangle or square, and then P distance is just some side.
We're taking a magnitude in both cases, right? We take a magnitude here to make that a distance, right? Over on this side, you're right. This is a vector, but I'm not saying it's equal to the vector. I'm saying it's equal to the magnitude of that vector, because that magnitude is the area.
Okay.
Yeah. All right, yes.
I guess also along the same lines, I'm a little confused as to how the cross product is equal to just the p vector.
How the cross? I didn't understand.
Like the cross vector of p and w, how that's equal to just the magnitude.
Oh, no, it's not. No. The claim is that these two things are both equal to the area,
And they're not
right?
equal to each other.
They're not equal, and so therefore they are equal to each other, but that does not mean that this is equal to that. No, not at all.
Okay,
it's
so
this product. Yeah. So the thing that we want then, this is what we're trying to solve for, and you would get that by taking this and you kind of cross divide. Yeah. All right. Okay, let's see the next one. This one's very nice. Again, I'm sure someone must have shown this to me long ago. And you want to find the distance between parallel planes. Again, there's lots of points in each one. Do I mean that distance or this distance or that distance? There's a bunch of different distances between the planes. Again, the understanding when you say the distance means the shortest possible distance, which of course would require that we talk about the perpendicular distance. So this one's kind of a layup, frankly. Because this distance that we're interested in, let me do this in green, that distance that we're interested in is a component. Very easily a component. Just take any 2 points and subtract, right? 1 point in each plane, of course. Subtract, that gives you a vector, which is not what we're interested in, but its component in the normal direction is exactly this distance that we actually want, right? So if the component in that normal direction is the perpendicular distance. So again, very convenient, very slick move, nice tool for your toolbox. And yeah, handy. Alrighty. This is a tricky one. This one's really quite tricky. How to find the distance between skew lines. If you haven't seen this phrase before, skew lines means lines that do not intersect and are not parallel. It's sort of a worst case scenario of a pair of lines. Nothing good happens. Depending on how you look at it. So two skew lines. The slick move is to observe that the two direction vectors, if you were to take a cross product of them, the cross product's going to be perpendicular to both of those lines. That means that cross product, I can use that as a normal vector for planes containing those lines. Everybody see how that geometry works? That's just a neat observation, right? I mean, both of these purple planes that I define like this are parallel to both of those V1 and V2 vectors. So, neat move. So, the question then of how do I find the distance between two skew lines, how do I find this, sort of, perpendicular at both ends, distance between those two lines? Well, that distance is literally the distance between two parallel planes, and we've already solved that problem. So then you just use the method above that we just talked about. So another slick move. Again, I wish I'd thought of it. Somebody showed me long ago. Okay. All right. So that finishes up 1.5. We move on now to 1.7. Don't forget we have already done 1.6. We did that first day of class. Moving on to 1.7. Real quick. So what we're going to be talking about is coordinate systems. And y'all have seen rectangular coordinate systems. I just want to sort of doff the cap real quick to what rectangular coordinates are and how nice they are. Partly so that I can then point out that, you're going to have to let go a lot of that niceness that we won't get to enjoy with our other coordinate systems. So rectangular coordinates, we all love them. Rectangular coordinates are like this, right? And conveniently, they are what I'm going to call unique. For every point, there's exactly one pair of coordinates. It's not like you have, I could express this point's location in rectangular coordinates in various different ways. No, not at all. If there's a point in the plane, it has exactly one x coordinate and exactly one y coordinate. Full stop. Right? Okay. Not so in our coming new coordinate systems. So that's bad news. Sorry about that. Some other things that we are really accustomed to, and it's going to be a little bit of a drag to let go of this because it's so handy, right? But there's this really cool fact here that when you have a point, notice that the coordinates of that point are the coefficients in a linear combination of the standard basis vectors that gives the position vector for that point. All right, real neat little convenience. So that's nice. Tragically, a peculiarity of rectangular coordinates. You can't do this or anything like this in like polar or spherical coordinates that we're going to talk about soon. Likewise, here's one that we've gotten really spoiled by, right? I mean, it's very convenient that we can take a linear combination just taking the linear combinations of the coordinates. We compute linear combinations of vectors coordinate-wise. Just look at one coordinate at a time. It's nice and convenient, right? And again, not so when we get to non-rectangular coordinate systems. So sad that we have to let those things go, but so be it. All right, so first coordinate system is called polar coordinates. I think a lot of y'all may have seen these before. You can define these coordinates without creating a function. I think it's valuable to think of them as inputs to a function. So the function in question is this right here that says if you give me an r and a theta, right, you put those numbers in to this function and out comes a location in the xy plane, namely an x and a y. Now how does this function work? Well, the idea is that whatever your r is, let me do theta first. Whatever your theta is, that tells you how far, let me do better than that, how far you should turn counterclockwise from the positive part of the x-axis to define a direction. So that's what theta does in this function. And then what r does, r says, and I'm gonna deliberately commit a little math crime here, just for the sake of broad strokes and initial convenience, and then I'll fix it in a moment. R says how far do you go in that direction? So I probably shouldn't make that look like a vector, should I? So that says how far you go in the direction defined by theta. Okay, now let me confess to my math crime. I said how far. That sounds like a distance. Tragically, distances are positive. R does not have to be positive. R is totally allowed to be negative, right? So said differently, R is not a distance, it's a coordinate, right? So think back to rectangular coordinates. The x coordinate is not a distance, right? Because x could be negative. There's nothing wrong with x being negative. But just negative means that you go to the sort of the left side of the x-axis instead of the right side, right? So make sure to be clear in your mind the difference between a coordinate and a distance, right? They're closely related, of course. If you know the coordinates, then you can compute the distance, right? But the coordinate and the distance, they're different things. Okay, so R, being as is a coordinate, technically isn't a distance. It doesn't actually tell you how far exactly. You just have to remember that if R is negative, you just go the other way. Right? Just go what you might call backwards. Go opposite of the direction defined by theta. Is that cool for everybody? All right. So thus the quotes that I put here, the sort of confession that I'm being sloppy there, but very convenient for sort of first strokes. Okay, now there's a little bit of geometry that y'all can do on your own. I'm going to leave this as a hopefully easy exercise for y'all. But you draw this triangle for example, or think about the unit circle if you prefer. It's honestly a little bit better to think about the unit circle. But anyway, easy persuasion. I hope that x is r cosine theta, right? And y is r sine theta. So make sure that you can do that. Make sure you're comfortable with that reasoning. Again, it's just a little bit of trig, and there you go. All right, everybody happy? Okay. So now here's a few warnings, a couple of landmines that you should be aware of. So be careful not to step on. They're not unique, right? As promised. Not unique. Any given point in the XY plane, let's say this point right here, there's a bunch of different ways to describe that with a direction and I can't say distance. A direction, a theta and an r, right? There's different ways to do this. So the obvious way to do it is to say, all right, well, look, we've got an angle that I can kind of see right there. Let's let that angle be theta. And then let's see here. Let's suppose that this is 5 right there. And so 5. Then this point here, that r and that theta, are giving you the polar coordinates of that point right there. How we doing? Okay. Here's the thing. It seems silly, but you gotta give me that if I were to add 2 pi to the angle, 2 pi is just going to take that theta direction that we were just talking about. 2 pi will say, okay, well, yeah, but we're going to go around another full turn. And here's the thing. If you go around a full turn, you're back to pointing in the same direction you had been. So adding 2 pi to the polar angle kind of does nothing. So this is a different set of what you might call polar coordinates for this point. So again, this point here, you could describe it with sort of the obvious theta and r, or you could go around a full turn and describe it with that, or another full turn after that. Right? You got a lot of options. So there's a lot of ways then in which polar coordinates are not unique. And we're not even done yet, but already there's infinitely many. Is everybody with me? All right, so here's the other one, and this is annoying. So what would happen if we went up by just pi? Said differently, if we were to add just a half turn to the direction, right? So we were looking at, initially we were looking at this angle, theta, there. And if I add pi, let's see here. I guess I'll use dark green. Angle now being theta plus pi. I claim I can get to that purple point with this dark green direction. And what you got to keep in mind here is that, again, r is allowed to be negative. So obviously, by going this actual direction, interpreted strictly, obviously that's not going to get me to the purple point, right? But if I just say, okay, well, let's let r be negative 5, right? That says, okay, I'm going to go in that dark green direction, but backwards by distance 5, and sure enough, it gets me to the same point. So, also fine. Does that make sense to everybody? So, there's some ugly, sort of weird, confusing realities of polar coordinates that they're not unique, and they're not unique in a couple of different ways. So, heads up. Okay. All right. Next thing I want to point out, that this is just a matter of sort of sloppiness of notation, but so be it. This is kind of how people talk. People just write an ordered pair, and if they mean that these are the polar coordinates of the point in question, very often that's just, I don't know, it's if they didn't write it down, they don't technically say it, they assume that you interpreted them the way that they intended. This is unfortunate, right? So let's think about, what does 2 comma pi over 6 mean? Well, it could be that they meant that these are the polar coordinates. I mean, after all, pi over 6 looks like an angle. It feels like an angle. Right? And so maybe they meant this point here, but I have to point out that these numbers could be an x and a y. That value, pi over 6, that's a real number. There's not a special category of numbers called angled numbers that's somehow distinct from other linear coordinate numbers. It's a perfectly good number, and that could therefore describe a point whose x coordinate is 2 and whose y coordinate is pi over 6. Could be. Of course, these are different points. So, another sort of like landmine, heads up, be on the lookout for this. Now, when you're looking at what's written elsewhere, just like I say, just heads up. Be careful. When you are the one doing the writing, right? If you want to avoid this kind of sloppiness, which you should, ideally, just clarify. It's real easy to do. You just say r theta equals 2 comma pi over 6. Ambiguity gone, right? Perfectly clear what this means, and then we know it's definitely that. We definitely did not mean this. Very good. More landmines. Converting the other direction, right? Now, it's easy to convert if you have the polar coordinates and you want to find the rectangular coordinates. A little bit of trig, nothing to it, easy formulas. Okay. If you want to go the other way, it is a little tricky. It is counterintuitive. It is dangerous. Now, here are some true formulas. Easily confirmed. You can think of these as algebra, trig, or geometry problems, depending on how you want to look at them. But anyway, it's tempting to overwork the algebra. Tempting to write these as r equals, and I'm going to put a question mark here so I don't write something false, square root of x squared plus y squared. For example. So what's the difference? At a glance, you might say, oh, well, the one on top is, yeah, we took it all away. We solved for r. But the top formula is wrong. Okay, the top formula seems to say that R, is a square root. Square roots, that symbol I should say, that symbol right there means the positive square root. It does not mean whichever one you feel like. You got to be really careful, but that symbol means square root. That's why when you're using, let's say, the quadratic equation, for example, they will explicitly write plus or minus. If you don't put that in there, that means positive, right? So tricky, and be careful. I like to just leave it in this form right here, so I don't have to deal with that. And of course, I obviously know how to solve. I know how to get to the R, right? The fact that I need to take a square root of both sides is not a tricky algebraic move. So I think this is a cleaner sort of thing to write down and to view as being that's your formula, because now you can't, I don't know. Anyway, for whatever reason, I find this more comfortable. And then likewise here, very tempting to solve, quotes, solve for theta as arc arctan of y over x. Problem, this is not true. Arctan takes a very specific set of values. Arctan is always between negative pi over 2 and pi over 2. Theta is not in any such way restricted. So this is making inappropriate assumptions about theta. So you can't assume that. All right. So now let me show you an example that is a seemingly innocent example. I like the seemingly innocent ones because I think it's persuasive that, if the innocent ones have a problem, just imagine hard ones, right? So here is a point. Let's think about this point right here, -1, given in rectangular coordinates. And let's write this in polar coordinates. Well, these formulas right here tell us that r squared and tan theta are easily computed values. And then you can notice that, that means that r has got to be one or the other of these, and theta has got to be one or the other of these. And then notice I've got these plus 2 pi in, sort of recognizing that you can go around an extra 2 pi any number of times. It doesn't really matter, right? But that's not what I want to focus on here. What a lot of students will do on a question like this is say, I get to choose. Cool, I'm going to pick the most convenient values, and the most convenient ones are, of course, the positive square root and the smallest theta value, namely pi over 4. And the problem is that point's over here, which is not what we want. Everybody see what I mean? So what I believe that this example dispels pretty persuasively is this idea that you can solve for r and theta purely with algebra. You're going to get a wrong answer. It's not my fault. Don't believe me, right? I'm just saying. Check it out. I mean. So please do not try to do this just entirely with algebra. You also have to look at the geometry of the situation, right? This is essential, right? The algebra will give you some candidate values that maybe not, I don't know, but the geometry is what will help you decide which one or ones or what combination is the one that actually works. So, for example, that actually works, right? That gives me a theta and an r. That get me to the correct point. Sorry. But this was the one that was wrong. Sorry. That's wrong. But this combination here is right. Everybody on board? Yeah. Okay. Yep. Okay, some quick examples of equations. I don't want to spend a lot of time on this. This is pretty easy algebra. If you have if you have a polar equation, you can convert that into a rectangular equation. And sometimes you don't really need to. I mean, let's look at this polar equation right here. R equals 3. That's just telling me that it's telling me R is positive. that means that this r is literally a distance. So it's literally telling me that the distance from the origin is 3. I know that that's a circle. There's not, I mean, this is not a challenging, interpretation in this case, right? So kind of a freebie. But if you hadn't noticed that, if you wanted to do this algebraically, notice what you can do is square both sides of the equation. And that makes the left side something that we have a pat algebraic rule that allows me to rewrite it in rectangular coordinates. This is, how this particular cookie crumbled, right? It's always going to be a little bit different. Here's another one, theta equals pi over 3. Again, you know what theta means. You know what about directions and blah, blah, blah. You could figure that out on your own, just a little geometry. But again, if you hadn't noticed, in this case, the tricky move, it's always different, but the tricky move in this case, take the tangent of both sides, and then notice, tan theta. I have a pat formula for that. Tan theta is y over x. And that then gets you to a arguably more conveniently recognizable equation for that line. Okay. All right. Now here's one that's harder. This one you can't really do algebraically, at least not in practice. But let's try to understand this equation here, r equals sine 2 theta. Sometimes you just have to go through and plot points. Rather than plotting actual points one at a time, a finite number of points, I like to kind of think, one group of angles at a time. This is just a point of view, but let's think about, sort of one quadrant at a time, if you will. So as theta goes from 0 to pi over 2, what am I going to do for these angles? Theta goes from 0 to pi over 2. Now do keep in mind, theta is not what we're plugging into the sine function. Into the sine function, we are plugging, you can see right there, 2 theta. Really easy to mess those up. It's really easy to, in some sense, use mathematical pronouns sort of too much. Be like, oh, theta, the angle, there's multiple angles in this question. There's theta, which is geometrically relevant, and there's 2 theta, which is what we're plugging into sine. So don't think about the angle when there's more than one angle. Very dangerous. So, okay, well, let's think about 2 theta. The argument that goes into the sine function. 2 theta goes from 0 to pi. And as 2 theta goes from 0 to pi, we know what sine does. Sine does that trick. The values of sine start at 0, they make their way all the way up to 1, and then they come all the way back down to 0. And so now we've actually got something we can kind of plot, right? I can think about all these different values of theta, right, from 0 to pi. 0 to pi over 2. Sorry, careful. See how easy it is to mess up? So as theta goes from 0 to pi over 2, the values of this function, the r, if you will, is doing that, which means I get kind of, it goes like this. It goes from 0 all the way up to 1. As the angle increases, then r starts to come back down, and so you can see you get something like that. What do you think? A little flower petal or something? Okay. All right, and then etc. You can play the same game for. Let's clean up the mess. Let's think about real quick as theta goes from pi over 2 to pi. Keep in mind that means that 2 theta goes from pi to 2 pi, over which values sine starts at 0, goes down to -1, and then back up to 0. Okay, so now this is going to be a little bit geometrically confusing, but you got to remember as we're doing this now that for an angle, let's say like that, for that value of theta, right? The corresponding r because that R is negative, you're going to be going backwards. Right? And so as we go sort of, again, counterclockwise across the second quadrant there, we end up with something kind of like this. Oh gosh, these are horrible lines. I'm sorry. You get the idea. Everybody happy? Okay. Now it's a nice exercise. I'm going to leave it as an exercise for y'all to persuade yourself that altogether what this curve does is it goes like that, and then it comes over here, and then it comes over here like this, and then goes back to the origin. So it makes a little four-leaf clover. It's kind of cute. Everybody happy? So think through the third and fourth quadrants. Make sure you're comfortable with that. Sort of the geometry of it all can be confusing. Okay, here's another nice little tool for your toolbox. This kind of thing comes up sometimes. How would I convert this to rectangular coordinates? Now you see the R over here, and you're going to feel a strong temptation to, R. Oh yeah, what I need to do when I see an R, I need to square both sides of the equation, because then R squared becomes something that I recognize, and yay, this worked well last time. Isn't that lovely? Okay. The problem is, if I square both sides, this becomes cosine squared, which doesn't ring any bells rectangularly, right? So the slick move here is not to square both sides. The slick move here is to multiply both sides by R. You get the same good news there, but then you also get good news on the other side too. Slick. Wish I thought of it. Everybody see the trick there? It's always, every one of these questions is a little bit different, right? But can be useful. Now I want to draw y'all's attention to a point of algebra, high school algebra, that I would imagine you've all seen, and I speculate from previous experience that you've either forgotten or possibly your high school teachers might have told you, yeah, you don't even know how to do that. But it's this thing called completing the square. Do y'all remember completing the square? Do you remember of completing the square? Yeah. Okay. So, high school teachers make all sorts of decisions, it seems, just, on the basis of whatever their experience is, that telling students what they do and don't need to know. I don't think that's at all appropriate. Of course you need to know how to do completing the square. This is a nice little example, to figure out what this represents, right? We take the x, we move it over to the other side with a minus, and this by itself is not a square. I've got to figure out what is it that I add to both sides of the equation to make this actually a square, right? And what it is in this case is 1/4, as it turns out. Right. So anyway, this knowing what the sort of the magic constant is to put on the right to make it turn into a perfect square, this is called completing the square. It's not deep. It's just a little point of high school algebra. If you don't remember how to do that, doesn't matter whose fault that is. Let's blame your high school teacher. They're not here, right? So let's say it's their fault, right? Anyway, one way or the other, you need to know how to do this. So look it up. I'm sure there's a bazillion websites on how to do completing the square, and make sure that you could do that. Noticing then that the result turns into a recognizable circle. So neat fact, R equals cosine theta is a circle. Very cool. Okay. Likewise, if you have sine, now I've done the algebra here a different direction, but sine also makes a circle. Now again, the algebra on this one does go the other direction. Here we're starting with rectangular and then moving back to polar. And this is really quite a bit easier, in fact, because all you got to do is kind of multiply out your square. And then notice that having done that, r squared showed up. How nice. Right? And then, of course, there's this y sitting here, but why in polar coordinates? Nothing to it. Right? So going in the rectangular to polar direction is really much more straightforward. And then there's just a little bit of you got to kind of think through that. How would you clean up that algebra most elegantly? And I think this is hard to beat. This is pretty standard. How you'd write that down. But anyway, go either direction. Algebra is different. Okay. Alrighty. Okay, let's talk three. Oh yeah, question.
So when you go from rectangular to polar, will the equation not be unique?
With the what now?
The final equation will it not be unique?
Oh yeah, I guess technically, if you wanted to replace this theta here with theta plus 2 pi or something like that, but you don't need to really worry about that kind of thing.
I mean, you wrote r equals 0.
Oh, you're talking about this thing over here. What happened there is as I was going from the left equation to the right equation, I canceled a factor of r. Canceling is dividing. Dividing is only legal if the thing that you're dealing with is not 0, right? And so whenever you divide by something that might be 0, you need to confess, ooh, I divided by something. So if that thing I divided by is 0, oh gosh, I what I've written down here does not recognize that possibility, right? And so this is just a sort of a kind of a half confession, recognition that I need to consider that separately. Now, conveniently, there are values of theta that make r equal to 0. Right, and there is only one point where r is 0, and so the problem's not really a problem, right? But that's just I just wanted to be careful algebraically. Yeah. Does that make sense?
So really, there's just one solution.
Yeah. I mean, this is the equation of this circle. Yeah, that's no problem. Yeah. Is that cool?
Yeah.
Okay, let's go to 3 dimensions. Cylindrical coordinates is the first one to talk about. It is regularly referred to as polar coordinates in 3 space or 3-dimensional polar coordinates, and I kind of support that in a way. It's literally polar coordinates for the XY projection. It's just X and Y, or r cosine theta, r sine theta, and all this is all regular polar coordinates for the projection of the point you're interested down into the XY plane. And we just have to then recognize that this point, though, also has, in addition to the r and theta representing the X and Y, there's also a Z coordinate that comes from, you might say, projecting over to the Z-axis. And we just keep it. That's it. Okay? So Z, the rectangular coordinate Z, is also the cylindrical coordinate Z. They mean the same thing, and it's just, it has to kind of stay there, because after all, we have a point in 3 space, and we can use r and theta to describe the x and the y, but we do need to also keep track of the z. Is that cool? So, reasonable to call this polar coordinates in 3 space, because it's literally using both of the polar coordinates. Okay, so a couple of quick examples, and then we'll move on to the more challenging spherical coordinates. But if you write down r equals c, you get a cylinder, thus the name cylindrical coordinates. That's an easy geometric pitch. Something to think about. Go ahead and think that through, right? Persuade yourself that this equation always gives you a cylinder. Okay. All right. A sphere, keeping in mind what we know about polar coordinates and therefore cylindrical coordinates. The cylindrical equation of the sphere is just this. R squared plus Z squared equals C squared. So, yeah. No big deal there. The next one's a little tricky. Z equals KR. It's tempting to look at this and say, oh, okay, well, this says that height is equal to distance from the z-axis, and that motivates a cone like this that a lot of people will draw like so and be done with it. And you probably heard me commit the math crime there. I said distance from the z-axis. Keep in mind, r is not a distance, it's a coordinate. Coordinates are allowed to be negative. R can be negative, which of course would make Z negative. And so there's stuff down here as well. And you can't forget about that. Now, here's a different point of view on it. I think this is a really nice point of view. First thing I'm going to do is I'm going to argue that this equation here is a rotation around the z-axis. I'm just going to make a geometric appeal here. The big thing to notice, no thetas in that equation, right? The cylindrical variables are r, theta, and z. I see the r, I see the z. There's no theta. Now, what does that mean when there's no theta? What that means is whichever value of theta you pick, whatever theta slice, oh gosh, sorry, my elbow does that sometimes. I apologize. It's very jarring. Whichever theta slice you might happen to be looking at, you get the same cross section. Because whatever theta is doesn't have any impact at all on the equation. So all of these different theta cross sections, they all look exactly the same. And then geometric appeal, if all of those cross sections look the same, you have a rotationally symmetric surface. Is that cool? Nice little fact to remember. Missing theta equals rotationally symmetric around the z-axis. It's a good one. That noted, what is it that's being rotated? Well, z equals kr. It's a line. If you look in the what you might call the RZ plane, right? Z is proportional to R, and so the bigger R gets, the bigger Z gets. Yeah. But then furthermore, if R gets negative, so does Z. And so we have that around there as well. And if you think about what happens if you then take that line, right, and then rotate around the z-axis, it generates this hole. You might say two-sided cone, if you will. Does that make sense to everybody? All right. Okay, let's talk about. Real quick. This is just a notational warning. Confusion of variables is a real problem. We only have so many letters to use, right? That's part of why we branch out and start using letters of different alphabets, like Greek alphabet, theta, and stuff like that, alpha. So there is a strong temptation to use R whenever you have a radius given. And here's the problem. There's going to be lots of radii. Right? So for example, let's suppose you have a sphere, and this sphere, you're going to take a slice of it, and that cross section will be a disk. Well, okay, let's say a ball, solid ball, cross section is going to be a disk, right? Well, now there's two different radii already in play. There's the radius of the sphere, not to be confused with what is the radius of the little slice, that disk that is the slice of that sphere. Two different radii, right? So, and then there's also, of course, the coordinate r. which we like to call r because it is the radius of a hypothetical circle. So you can't call them all r, right? So please be very careful. If there's something round in your problem that therefore has a radius and you would like to refer to that radius, don't use r unless you're quite sure you will not be using cylindrical coordinates. And even then, you still probably shouldn't call it r because your reader, grader, whatever, might think that you were talking about cylindrical coordinates or polar coordinates, right? So I would advise you've got various other options. You can use like R naught, or you could use capital R, right? Or you could use R of S for the radius of the sphere and R of C for the radius of a circle, or just not plain old vanilla straight up R. That would be a confusion of variables problem. Everybody see what I mean? I know it's annoying and seemingly trivial, right? But sometimes trivial things can create massive confusions, and you just got to be careful about that. Okay, now on to spherical coordinates. This is harder. Spherical coordinates, also sometimes referred to as polar coordinates in 3 dimensions. This I do not support. We've already got something that we call polar coordinates in 3 dimensions. They can't both be because they're different, right? So please, I think this is a very, very bad idea to think of this as being polar coordinates in 3 space. It's not. It's importantly different. Okay, so what is it then? These are the spherical coordinate variables, rho, phi, and theta. And let's walk through them one at a time here. Theta, good news. It's the same theta from cylindrical coordinates. So it is the angle measured in the usual direction from the positive part of the x-axis. The angle over to what I call the theta plane, or the theta, I guess it's a half plane, the theta half plane. And I like to call this, this is just a lingo thing for me, hinged on the z-axis, because you could imagine if this were a door, like as theta increases, this door, if you will, kind of swings around counterclockwise, and the hinges of this hypothetical door are on the z-axis. It's just like I say, it's a metaphor, and lingo motivated by the metaphor, but I find that satisfying. Everybody on board? Okay. Cool. So that's what theta is. Okay, now next we're going to talk about phi. That's the Greek letter phi. Phi is another angle, which seems weird. It's another angle, and it is defined as an angle measured off of the z-axis, measured toward the theta half plane, right? So not back this way, right? It's measured, the positive direction of phi is toward the theta half plane. Now, again, angles are allowed to be negative, right? Just like theta can be negative, well, so can phi. And a negative value of phi would be, well, exactly what you would think. It's, backwards from the phi, backwards from the theta half plane if phi is negative. Exactly what you would expect. Yep.
What is like a half plane extends into a normal plane?
A plane extends infinitely in all directions. A half plane, imagine that somebody cuts it either, now in this case vertically, right? But it could be, you could cut it horizontally, you could cut it in an angle, whatever. But if you cut it into 2 pieces and then throw one of them away, what remains is a half plane. We want to be careful not to overthink it, right? Because is it really half? I mean, they're both infinitely big. What did that even mean, right? So this is, we don't overthink. But the idea is we cut it into two. If you cut it into two equal pieces and throw away one of the equal pieces, I mean, right. Is that satisfying?
And it's cut along the z-axis.
This, yeah, that's right. So here with the half plane, the what you might call the cut edge of the half plane is the z-axis. Right. Cool. All right. So now notice with a theta and a phi selected, that defines a direction. And let's see here. Let me do this in green. Theta and phi together define a direction out of the origin. Everybody good so far? And then rho is the last one. That's a Greek letter rho. I know it looks like a P. It's not a P. You can't write a P if you mean rho. P will be other things, right? But this rho needs to be distinct. So, apologies. And I know it seems silly, but if you haven't made a comfortable practice of how to write these new Greek letters that you haven't seen before, it seems demeaning. But you got to sit there with some paper and just sit there and decide for yourself if you're going to be the kind of person who starts in the middle and sort of rotates out, or do you start on the outside and kind of rotate in? Everybody's different, right? I'm an outside in kind of guy, but whatever. I don't. There's no reason you have to. Just make sure that you don't write a P, because a P is not the same as a rho. P is not a spherical coordinate, right? So you gotta make a point of not doing that. So P says again how far, and again in quotes because it's not a distance, it's a coordinate, and so opposite direction if rho is negative, but it says in some sense how far to go, and thus with the direction having already been decided, that gets you then to a point. So that point there has spherical coordinates, rho, phi, and theta. Everybody good? Yep.
Is there a particular reason that it's rho phi theta and not rho theta phi for the spherical coordinates?
Yeah, that's pretty arbitrary. Some people might even do it in the other order. It doesn't really matter. So this is another example of where, if there's any possibility for misinterpreting, then go ahead and just indicate, like we did here. And just say literally, what are these things that you're telling me? Yeah. And that removes all doubt. You want to hear something really tragic? Not only do some people put them in different order, some people label them differently. There are those for whom this thing here that I call theta, they call it phi. And vice versa. The thing that I call phi, they call theta. So my memory is that physicists do it the other way, for example, right? Every math book I've ever seen, that I recall anyway, does it as I'm presenting it here. So it's all kind of arbitrary in some sense, but I just have to always be on the lookout for people who subscribe to a different convention. Okay. All right. Okay. So, how do you convert? Let's see here. I'm going to start with noting. Let's see here. I'll use green here. That triangle. Keeping in mind that this side here of the triangle is a projection, that means it's vertical. That means that this is a right angle. Right? Let's study this little right-angled triangle. And that's a right angle. So the good move, in my opinion, is to first observe that phi, there's our angle phi, is also this angle there. It's one of the angles of the right triangle in question. And I can very conveniently write down that R, just from the trig of that triangle, is rho sine phi. And this is actually a really powerful observation because we already know that x and y are cosine theta, r sine theta. Right? It's a real slick move. All you got to do is remember that little triangle, right? And I guess you could say you got to remember how that triangle fits into the picture up here, right? But if you just, understand that triangle, do just the tiniest little bit of trig, and we're 2/3 of the way toward writing down spherical coordinate formulas. It's hardly even anything else to memorize. It's just r cosine theta, r sine theta. You just have to remember what r is. Now, for whatever it's worth, I'm just this. Everybody's different, and what works for you might be different from what works for me. I'm very open-minded on this, but for me, I know that I will never be able to trust myself to remember this formula. I know that if I think I've got that formula memorized, there's a chance. It's just a question of time until that memory fades just enough that I might get it backwards. So I, in my life, have never memorized that formula. And, if you want to memorize it, cool, that's fine, right? But what I do every single time that I need to know these formulas over here, I think about that triangle. And I do the trig. It's easy, trig. Right? I trust myself to get the trig right. I do not trust myself to remember it right. Right? So suit yourself. A case could be made that maybe the safest move would be to both memorize it and be comfortable enough with this picture so that you can use the trivial trig to rederive it as needed. Also, right? Suit yourself, but again, I don't trust myself to remember it, and I therefore have not bothered in my life to ever memorize it. Okay, then of course we're a hop, skip, and a jump away. After all, the third coordinate is just the other side of this triangle. And there you go. There's your formulas for spherical coordinates, converting spherical coordinates. Everybody happy? Alrighty. A little quick example. Rho equals C is a very easy equation for a sphere centered at the origin, of course. Again, because this equation is so easy and fundamental, you might say, this is what happens when you fix, one of the spherical coordinates. That's a pretty natural motivation for calling it spherical coordinates. Okay. All right. Here's a nice little challenge problem. Most of this I'm going to let y'all think through on your own. I think this is healthy exercise. I don't want to. In order to learn things, you got to get in there and get your hands dirty and get some dirt under your fingernails, right? So what I think would be a really good exercise along those lines is to think through all four of the ways to represent a point in spherical coordinates. And again, we know they're not unique. Now, I say four. There's actually infinitely many ways to do this, of course, because you can always add 2 pi to any of the angles. In some sense, adding 2 pi kind of geometrically at least doesn't do anything. So there you go. There's infinitely many options. But aside from the adding 2 pi to your heart's content, there are 4 different ways to write most points in spherical coordinates. So let's think through some of this. So let's think about this point right here, right there. And you'll notice I've picked some convenient numbers. That distance is 1. That distance is the square root of 3. That makes that distance 2. That distance there being 2 makes this angle conveniently identifiably pi over 4, et cetera, et cetera. So the geometry here that gives us these angles and these distances is pretty boring. Just a little bit of geometry in 3D. So what do we do with that information, though, to describe at this point? Well, so of course, one thing I could do is I can think of this point as being in this theta plane, where theta is pi over 3, for example. Right? And with theta equaling to pi over 3, I can see in this picture what my phi is going to be. Phi is, well, it's that angle, which is pi over 4. So, no problem. Is everybody with me? But let's recognize there are other ways that I could get to that same point. And here's one of them. Let's keep theta as pi over 3. And then let's recognize that this direction is kind of what I get when I instead of going that way by pi over 4, what if I went the other way by 3 pi over 4? Right? So keeping still using theta equals pi over 3, a negative value of phi. So this would be phi equals negative 3 pi over 4. Ran out of space. Gets me going the exact wrong way, which means that I can get to where I need to be with just a negative value of rho. Here I would have rho, let me just say negative, I don't have the space, but negative, whatever that distance is, 2 root 2, I guess. So that is a different, perfectly valid, different set of spherical coordinates for that point. Everybody happy? Okay, so the exercise that I want y'all to do is to fill in the blanks for the other two. The other two are going to come about by using, instead of this value of theta, they're going to come about by using the other value of theta, where we rotate all the way around over to there, like that. And with theta being 4 pi over 3, in other words. Now, what are the different options? What is there a positive value of phi that would get me? Is there a negative value of phi that would get me to the what is rho positive or is it negative? Nice exercise to think through. Everybody see what I want you to do? Okay. All right. I think this is a fun little exercise here. This is about latitude and longitude on the surface of the Earth. We're going to pretend, for the purposes of this question, that the Earth is a perfect sphere, which is, pretty close. Not quite. We're not going to worry about the slightly oblongness of the shape of the Earth, or the ups and downs of mountains and valleys and stuff. I would ignore all that. So what we're going to do is we're going to set things up so that the North Pole is at the where the z-axis emerges, and the center of the Earth is at the origin, and the prime meridian is where the positive part of the x-axis is. So just kind of the most convenient setup that will allow us to relate spherical coordinates to map coordinates, longitude and latitude. So that being the case, notice that what we're calling theta is literally and exactly east longitude. That's what east longitude is, right? Okay. So that's handy. Now, not quite so convenient for latitude. Latitude is measured upward from the equator, right? North latitude measured up from the equator. Phi is measured downward from the North Pole, you might say. So latitude and phi are not the same. However, it's pretty easy to notice that they always add up to pi over 2. And so it's pretty easy to write phi in terms of latitude, even if they're not exactly the same. Is everybody with me on that? Okay. All right. So with these observations made, and of course every point on the surface is a distance from the origin given by, well, the radius of the Earth, which again, we're ignoring the fact that that's not, this actually depends on phi pretty significantly. The tune of something about 40 miles, if I remember correctly. It's quite a lot, actually. Anyway, this allows us to solve what would otherwise be an extremely difficult problem. How do I compute the distance as the plane flies between 2 points on the surface of the Earth? So here's why that's a hard problem. For one thing, notice this is not a Pythagorean problem. We are not going to tunnel under the surface. Right? It is not the same. Secondly, we're not going to, follow a latitude line and then from there sort of go straight up like that. That would be relatively easy to compute the distance of that purple path. That's also not what we're going to do. Furthermore, this path that we are talking about following, whatever that shortest possible path is along the surface, this is not a right triangle. It's just not, right? So, we've got a what are we going to do kind of a situation. So, lovely argument is to realize that all we really need to do is to figure out that angle. Right? Once you know alpha, and we know the radius, right? The arc length that we're interested in is just radius times angle. That's an old geometry formula. I hope everybody remembers that one. It does bring up the question, though, of how on earth am I going to figure out that angle? And how we're going to figure out that angle is, this is where the cleverness comes in. The cleverness is to recognize that if I know longitudes and latitudes, which of course we do, right? Google Maps will tell you the longitude and latitude of any location on the surface of the Earth that you want. Cool. Well, once you've got longitude and latitude, you've got spherical coordinates per the upper part of this page. Once you've got spherical coordinates, you've got rectangular coordinates per the previous page. Once you've got rectangular coordinates, now you can compute the dot product. Right? Again, it's three-function arithmetic. Dot products and rectangular coordinates, nothing to it. Then we remind ourselves, dot products can be computed in terms of lengths and angles. Well, again, these lengths are both the radius of the Earth. The angle here is exactly the angle that we're looking for. And then you just solve for alpha. Solve for alpha, and then we're in business. So let's just move, right? Really, really cool, really clever calculation. All right. Okay, I'm going to say real quick, super quick thing. Again, you can convert from rectangular coordinates into spherical coordinates. It's the same trick of just don't forget that you have these conversion formulas already, right? X squared plus Y squared plus Z squared. That is rho squared. And X is, from the first discussion we had on this topic, rho sine phi cosine theta. And so, in some sense, if you just kind of multiply everything out and then plug in, then, and then be careful, move things around appropriately, then you get the spherical equation. Okay, so I'm going to say some quick things about this, and then we're going to call it a chapter. So we will be finishing chapter 1 here in the next 25 seconds. Standard basis vectors we've talked about. These, though, are what you might call the rectangular standard basis vectors. There are also polar standard basis vectors. So the unit vector pointing in the direction where r is increasing. And then there's a unit vector pointing in the direction where theta is increasing. And you can write down formulas, just a little bit of geometry there. So we're actually not going to be doing really anything with these vectors in this class. The formulas for them are all written down. They're here. They're also in the book. And it's, I suppose, a nice little geometry exercise to think through. So, maybe spend a little time thinking through and try to persuade yourself that you understand where all of these come from. But I don't want to spend valuable class time on, deriving formulas for things we're never going to use, right? So you may use these elsewhere on other occasions, and again, here they are. And just be aware, they are not as nice as rectangular standard basis vectors. For one thing, they're not constants. They move around, right? Depending on where you are, they point in different directions. So that's annoying. Then, again, the algebra doesn't work nice. You would think something like this would be true just because that's true, but this isn't. So, again, we're not going to be doing much with them. When you do ever in the future, if you do ever do anything with them, be careful. Don't play too fast and loose with those things. Okay. All right, and I think that's all we need. Yeah, that's all I'm going to say about that. Okay, we're done with Chapter 1. Y'all have a good rest of your Monday. See you tomorrow.